So, welcome back everyone. Today we are going to rotational dynamics numericals. And before the video starting, I would like to give shout out to our new subscriber, Utkrishta Shrestha, and our first commenter, Siddesh Tiwari. Shout out to both of you. And now let's begin the video. For numericals, we are taking this book as reference. We will do numericals from this book, and though in exam the past year questions, this book is very useful. So I am not going to do the numericals from this book because it's the same thing in the both numerical books. So after you watch this video, try doing the numericals from this book yourself. Then you can test your understanding and everything. Yeah, so let's go to this book. Okay, this is the first chapter, rotational dynamics. There are a lot of solved examples as well. If you want, I can give you the solved photos of the questions. Okay, now we're going to exercise straightly. And by the way, there are type 1. There are different types of numericals. Type 1 is based on moment of inertia. Type 2 is analogy between rotational and translational, that is linear motion. And we have type 3, that is conservation of angular momentum, as you can see. And then we have higher ability questions. So we're doing all of them in this video. Stay tuned. Wait a minute. Okay, so we are starting with the first type numericals, and that is based on wait a minute, let me zoom a little bit. Yep, based on based on moment of inertia. We are doing some questions from example. Okay, there are 5 questions given, so we are doing a very good question. Which one? Let me see. Okay, this is a question number 4 from the book, if you have one. This looks like a good question. What does the question say? Let me write down the question real quick. The 3 are located at the vertices of an equilateral triangle of length A. What is the moment of inertia? Of the system about an axis along the altitude of the triangle passing through M1. Okay, so you can make a figure because there are three vertices of our equilateral triangle. There is an equilateral triangle just like this one, and the 3 vertices are M1, M2 and M3, and of length A. So it is A, all the sides are A. What is the moment of inertia of the system about an axis along the altitude of the triangle? First of all, what does this mean? Altitude of the triangle. This means the maximum height or the height of the triangle. That is this it is either this or this, or like this. Look at this, from M2 or from M3. It's the same way from all the parts in the equilateral triangle, but in question it's given from M1. So we are doing it like this. This is the axis. This is the axis of rotation. So we need to find what is the moment of inertia. So we know that what do we know? We know that moment of inertia is equal to, what is it, mr square, or we can write summation of mr square here, because there are many things. So let's do it. First of all, wait, we need to just know this much. We know masses are given, but we don't have radius. We need to find out the radius. Since this is a and this is the axis, how can we find out this radius from the axis? How can we? And also this one, this is the shortest path. This is the radius. Let me write down the radius. This is the radius. This is also the radius, and this will be also equal though. These will also be equal. So how can we know what is this and what is this? The question made it easy for us. Since all of the sides are a, this is basically a by 2. This is also a by 2. If the question had not given anything like that, we need to go further to Pythagoras theorem and other big shits. But right now we don't have to do anything like that. We can simply assume that much, and now we can just write m1 into the radius is 0, because this lies in the axis. As you can see, this lies in the axis, so the radius is 0. That is m1 into 0 plus m2 into a by 2 squared, mr squared, right, plus m3 into a by 2 squared. So this will be ma square by 4 plus m3 a square by 4. If you take a square by 4 common, then mi will be equal to a square by 4 times m2 plus m3. This is the moment of inertia of the triangle as given by the question. This type of question is very less likely to be asked in an NEB examination. This most probably won't be asked in your exam. Very less likely. However, we need to go to the more important ones, and to do that, we are now going to the next type of numericals, and that is analogy between translational and rotational motion. So these questions are like those questions in translational, but in angular momentum, like in rotational. So we're going to type 2 now. There are 6. No, there are a lot of questions given. Oh my god. There are 21 questions given of this type. So we already know that this type is the most important. And so now we are going to do like 3 to 4 questions from this 21. I'm going to select on random, or the ones that look appealing to me. Okay. And look at this. The book says that this was asked in some NEB exam. This was also asked in some NEB exam. Also, this was asked in NEB exam as well. This, also this, along with this one, just right there. Where is it not focusing there? And right here you can see, right here as you can see, right here as you can see, right here. Every question given here is asked in NEB. So all of them are equally important, but we cannot solve all of them. So We are going to do question number playground of merry-go-round is 2 meter has inertia and it's rotating is okay. Yeah, we're going question number 3. So let's go to question number 3. What does it say? Question number 3. A playground merry-go-round of radius 2 meter has a moment of inertia has a moment of inertia 250 kg square and is rotating at 10 revolution per minute. A 25 kg child jumps onto the edge of the merry-go-round. What is the new angular speed of the merry-go-round? So this is a very straightforward question. We have given, just write the given first. And about the formulas, I have not given a formula list, so you either look at the book or just learn it by the time doing this. A playground of merry-go-round with radius, so we have given r is equal to 2 meter. Moment of inertia I is given 250 kg meter square and rotating at, okay, now this is the thing, rotating at 10 revolution per minute. This looks like revolution per minute, that is rev per minute. What is this? So this is the unit of frequency. You need to know that this is frequency. Revolutions per minute is frequency, it is not angular speed. So we have given frequency is equal to 10 rev per minute. You quickly change it to a rev per second for easier calculation, because frequency is 1 upon time and time in second is more applicable today. So you just do 10 by minute into second is how much? 60, is it? Yep. Rev per second, this is 1 by 6 rev per second. Now first we need to find the initial angular velocity, because it, oh no, we don't need to, we need to find the new angular speed. So to do that, we need to assume that there is no external torque, and the question says nothing about it, so we will also assume that there is no external torque. Then we need to find omega first. Initial speed omega will be how much? If we don't know this, you will know now that omega is equal to 2 pi f. This is a relation, so we can write 2 pi f. This is 2 pi for the circle, total displacement in circle, and frequency. So this will be, it is basically, it's so simple, like this is in meters and this is in seconds. How circle, the whole displacement, if a body goes from here all the way through here to again comes here, then the displacement covered by it will be 2 theta. The whole angle is 2 pi, and 2 pi, that is, this is 360 degrees. So we use 2 pi for that, and f for the frequency, because the unit is meter per second. So yeah, it will be 2 pi into 1 by 6 rev, 1 by 6 the angle of omega is of course meter per, radians per second, because this is radians, not meter in angular. This can cut, so this will be pi by 3 rad per second. So we need to find what now? Now we need to find the initial moment of inertia. $250, is it? Oh yep, 250 kg meter square. So now what do we need to do is, from the principle of conservation of angular momentum, what do we have is I1 omega 1 equal to I2 omega 2. We know this much, don't we? Yep, we do. So yep, it is visible. So what can be done is I1 is given, that is 250, and omega 1 we just found out, that is pi by 3, and after that equal to I2 is not given and omega 2 is not given, but we know that I2 can be found out by mr squared. Is it not? Is it not? We know that we can just do oh, this is crazy. Look at this, what happened here. mr square plus I1 omega 2. Why did this happen? In this merry-go-round, the initial mass of every particle and itself was mr square. This was the moment of inertia initially. Since the radius, if the kid jumped in a constant radius where the other kids were also there, so the radius is constant, let's forget this, but the mass increased. So this is the inertia that it was added because of the boy jumping in it, and I1 was the normal previous inertia. So you add them both to find out the new inertia, and that will be 250 upon 3. Cannot be done. So 250 pi by 3 will be equal to mr squared is given, right? A child of 25 kg. 25 kg child is given, and at a merry-go-round with a radius of 2 meter, 10 revolutions per second is 2 meters given, right? Yep, 2 meters, yeah. Into 2 squared plus 250 was the initial, and omega 2. If you go for like this, omega 2 equal to 250 pi by 3 times 25 into 4 into 4 plus 250, then this will be somewhere nearby 0.75 rad per second. If there is any confusion, just tell me out. Look at this. 250 pi whole upon 3 times 25 into 4 plus 250. Yup. Or you can just leave it in the fraction form. So now we are moving on to the next question, and we are skipping question number 4 for now. Question number okay, here is the question. Everything is not visible, right? like this much, everything becomes visible on the page. Okay. The speed of a motor engine decreases from 900 rev per minute to 600 rev per minute. The speed of a motor engine the angular acceleration, number of revolutions made by the motor during this interval, and finally how many additional seconds are required for motor to come in rest in the same rate. Okay, now that we have the question, we are going to solve it. So the question said, look at this, the question has said that where is it? Here is the question. The speed of a motor engine, do not confuse that. If anything that is given in rev per minute or rev per second or something like that in revolutions per things, then this is frequency, this is not velocity. So what you can assure with this is so what can be done is first, for first question, the question asks to find the angular acceleration. Let's write the given things. Okay, from frequency, first frequency is 900 rev per minute equal to 900 by 60 rev per second, and 90 by 6 is 15 rev per second, and F2 is given 600 rev per minute. This is 600 by 60 rev per 10 rev per second, as you can see. So that much, yep, now you can see. Then what else the question says? Time is given 10 seconds, and the time is given 10 seconds. We need to find the angular acceleration. To find the angular acceleration, we need to find the omega. So firstly, we need to find the omega. To find the omega, we basically do omega 1 equal to 2 pi f1 and omega 2 equal to 2 pi f2. This will be 15 to 30 pi, and this will be 20 pi radians per second. Now we know that angular acceleration which is denoted by alpha, is basically omega 2 minus omega 1 by t, and this is 20 pi, 30 pi, how much will be 10 pi by 10, that is how much, let me calculate in the mind, let me quickly calculate in the mind. Okay, it's just omega, I think, I mean it's just pi, okay, yeah, it is pi. radian per second. This is like 3.14 radian per second square. You cannot use the absolute sign and just write negative pi because it is retarding, or you can just write it is retarding with retardation of minus 3.14 radian per second square. After that is done, what is our next job? Oh no, is it visible? Is this visible? Let me fix this. Wait a minute. Okay, now it's visible, probably. Okay. So we know that it is retarding with certain velocity, certain acceleration, which is the answer. This is the answer to the first question. Now let's look at the second question, which says number of revolutions made by the motor during this interval. We need to find number of revolutions. Number of revolutions. So number of revolutions. What is number of revolutions is that how many times is it completely revolving. So it is definitely related with displacement, and when it comes angle we can simply write 2 pi theta. Oh sorry, n. Number of revolutions is 2 pi theta. Oh my bad, it's not theta. Total displacement is 2 pi n. That is what you need to remember. Theta is equal to 2 pi n. So to find number of revolutions, we just need to use the s equal to ut plus 1 by 2 at square. This is what we need to use. So because there is theta, and theta is 2 pi n as said earlier. So theta is 2 pi n and will be equal to omega naught, that is the initially it is 900, so that is 30 pi, and the time taken is 10 seconds, plus 1 by 2 alpha we just found out is minus 3.14, and t square is 10 squared. From here we can find out n is 30 pi into 10 plus 1 by 2 minus 3.14 into 10 squared upon 2 pi. You can simply put it in the calculator just like this. And the answer you see is somewhere around 125.012. So you can just write this is equal to 125 revolutions. This is another answer. Now we go to the next and third mini question of the question, which asked us how many additional seconds are required for the motor to come to the rest at the same rate. Here the rate means acceleration or retardation. So at the same rate, that means alpha remaining minus pi radian per second square, how much more time would it take, or let's do this t prime, would it take for the thing to, so that its initial becomes the omega 2 equal to, how much was it? I think it was 10 pi. For this to come to rest at omega 3 becoming 0 radian per second at the same acceleration. Now you already know what we are going to do. We are going to do the AT relation. What is the AT relation? V equal to U plus AT, that relation. So V is the final. V is omega 3 equal to U plus AT, and here we have 0 is equal to omega 2 is 10 pi, alpha is minus pi into T is we need to find. So pi T is equal to 10 pi. T is equal to 10 pi by pi equal to 10 seconds. Okay, that's it, as you can see. Oh, it's not 10. Oh my god, sorry bro, it's not 10. Omega 2 is not 10. Oh ho ho ho. Oh my god, this is crazy. It is not 10, it is 20 pi, so we need to write 20 here. Everything is same, just change the value. Yeah, 20. And you have the answer right there. So you have all three answers, and that's question number 4 done. Now we're going to question number we're going to question number 11. Yeah, we're going to question number 11. We'll do one more after this, and then we'll move on to the next type of numericals. So wait a minute until I look at the question once. So let me copy the question. A constant torque of 200 newtons on tons of wheel. A constant torque of 200 Newton meter turns a wheel about its center. The moment of inertia about this axis. The moment of inertia about its axis is 100 kg meter cube. Find at the first number the angular velocity gained in 4 seconds. Gained in 4 seconds. And the second number, the kinetic energy gained after 20 revolutions. The kinetic energy gained after 20 revolutions. So first of all, the thing is given that torque is given here. So we cannot use principle of conservation of angular momentum in this question. So it is 200 Newton meter. Turns a wheel about its center. The moment of inertia about its axis I is given 100 kg meter cube. Find the angular velocity gained in 4 seconds. So this is very simple question. We know that torque and inertia are related as tau equal to I alpha. So tau will be equal to 200 equal to I is 100 alpha. So or we can just say that alpha is 2 radian per second square. Now that we know alpha, and we need to find what do we need to find the velocity, then we also know that angular velocity is related to alpha. So what can be done is, we know that alpha is omega by t. So alpha t will be equal to omega. 2 into 4 will be equal to omega, that is 8 radian per second. This is the value of omega. We now have the question of first answer done. The angular velocity gained in 4 seconds. But now we need to find the kinetic energy after 20 revolutions. So after 20 revolutions, 20 revolutions is the value of n equal to 20. So we can find the value of theta, which is 2 pi n, which is 20 into 2 is 40, right? 40 pi. Theta is 40 pi. Now we just use the equation of motion, that is theta equal to u did omega naught t plus 1 by 2 alpha t squared. So this is given as 40 pi equal to omega naught. First of all, omega is 8, right? Or we use 0. Let me check in the book. Oops. What is the book doing? The book is doing completely different thing. The book is finding the angular velocity first. After 20 revolutions for the... Okay, yeah, we need to do that too. So that is, we need to find the angular velocity. So we need to use the omega square, v square equal to u square plus 2a theta. That is omega square. Omega square is, this is not the omega, this is the omega naught, by the way. So we need to find the omega equal to under root 8 squared plus 2 alpha. 2 into 2, alpha is here, right here. Can you see here? Alpha is right here, and theta is 40 pi, which will give us that omega is somewhat equal to 22.42 radians per second. Now we can simply find the kinetic energy. Kinetic energy as 1 by 2 I omega squared, which will be 1 by 2, and I is not given, right? Is I given? I is not given. It should be, oh yeah, here is I, 100 into omega 22.42 squared. This will be somewhat around 25132.7 joules. This is the answer. Okay, so we are now going to question number 15. The question says, what the question says is pretty simple. The question says that a disk of moment of inertia, a disk of moment of inertia 4 kg meters cube square about its center rotates steadily. About its center rotates steadily about the center. What the hell? About the center and the mass of 5 kg. About the center Okay, here is the question. As you can see, a disk of moment of inertia 4 kg meters square about its center rotates steadily about the center and the mass of 5 kg. The velocity along the plane is 2 meters per second. If the radius of the disk is 2 meters, find the angular velocity and total energy of total energy. We know that omega is given 2 meters per second. So we know that from omega we can easily find the velocity. What do we need to find? The angular velocity. Find the radius. To find the radius, we can simply use it. Okay. This is a bit different question. You need to read it very thoroughly to actually understand what is happening. So the angular velocity is given as 20 radian. Okay, is it 20? No, it's 2, right? Yeah, it's 2, right? This is the most common misconception. You write omega equal to 2 meter per second. This is not correct. Omega is never in meter per second. So that is V. That is the translational velocity. Translational velocity along the plane is 2 meter per second. And with that, radius is also given. Radius is 2 meters. So omega is very easily found out to be, what is omega? V by R, because V is omega R. So V by R, that will be 2 by 2, that will be 1 radian per second. This is the angular velocity of the disk. Now for the total energy, this is the one number. Now for the total energy, it is Ke plus Ke rotational linear. Ke translational plus Ke rotational. So this will be 1 by 2 mv square plus 1 by 2 I omega square. So in this thing, we have mass, we have velocity. We do have mass, right? Yeah, we have mass, velocity, we have moment of inertia, we have omega. So we can simply put in everything, and the mass is given 5 kgs, and oops, the mass is given 5 kgs, and what else is given? Wait a minute. The velocity is given 2 meters per second, and the moment of inertia is given 4 kg per meter square, and the omega we just find out is 1. So this will exactly be equal to 12 joules, which is the answer. You can see 4 5 are 20 by 2, you do all, that will be 12. And that's how we do it. Now we're doing a last question for this kind of question, and we are doing the last question, so let's do it. I'm going to copy the question right here, and then I'm going to solve it on the page. It's visible, right? Is it visible? Let me rotate the gimbal just like that, a bit in forward direction. I'm going to write like this, so a bit more forward. Okay, now it will be visible. So question number 21 we're going to do now. A horizontal disc this pen is not right in top. A horizontal disc, you know the pen. Look at this, look at this, look at this. Crazy, isn't it? A horizontal disc rotating freely about a vertical axis. About a vertical axis makes 100 rpm. Makes 100 rpm. A small piece of wax of mass 10 kg. A small piece of wax of mass 10 kg falls, 10 gram, my bad, 10 gram falls vertically on the disc and adheres to it at a distance of 9 centimeter from the axis. Distance of 9 centimeter from the axis. If the number of revolutions per minute is thereby reduced to 90, calculate the moment of inertia of the disc. Calculate the moment of inertia of the disc. So let's read the question very thoroughly. A horizontal disc rotating freely about a vertical axis makes 100 revolutions per minute. A small piece of wax of mass 10 gram falls vertically on the disc and adheres to it at a distance of 9 centimeter from the axis. If 2 revolutions per minute is thereby reduced to 90, if the number of revolutions per minute is thereby reduced to 90, calculate the value of moment of inertia of the disc. So in this question we first write all the things. Here the question has given that first it is 100 revolutions per minute. Revolutions per minute is frequency, I said you earlier as well. So frequency 1, initially it is 100 revolutions per minute. So that will be as 100 by 60 revolutions per second. This will be 10 upon 6. What will be 10 upon 6? 10 upon 6. 5 by 3 revolutions per second. This is frequency first, and the final frequency 2, is 90 revolutions per minute, equal to 90 by 60 revolutions per second. So this will be 90 by 60, 3 by 2, 3 by 2 revolution per second. Now that we know this much, we can move on to the angular velocity. To find the angular velocity, we just can convert this like this: omega 1 and omega 2. This will be 2 pi f. This will be 5 into 2 pi f, 2 pi. This will 5 by 3 into 2 pi, my bad. It will be 10 by 3 pi, and this will also be 2 pi f, which will be 3 by 2 into 2 pi. It will be, this will cut, so there will be 3 pi. So we have the initial and final angular velocities as well. So after that, what we need to do, you can see in the question, a small piece of wax of 10 gram falls vertically on the disc and adheres to it at a distance. Radius r is 9 centimeter. This is 9 into 10 to the power minus 2 meters, and 10 gram mass is 10 gram, but we can write it in kilograms, that is 10 to the power minus 3 kgs. So now we can find out the moment of inertia that was added, or that was like increased due to this. Basically mr square, that will be 10 into 10 to the power minus 3 into 9 into 10 to the power minus 2 squared. This will be somewhere around 9 10 to the power minus 2 whole squared. 8.1 into 10 to the power minus 5 kg meter squared. Alright. Calculate the moment of inertia of the disk. This is the moment of inertia that was added to the disk, so it is I naught. We need to find the moment of inertia of the disk. So to do that, we just need to use the conservation of angular momentum. Okay, so we have, from the principle of conservation of angular momentum, I1 omega 1 equal to I2 omega 2. Here I1 is given as the first. There is no I1. The I1 is not given. We need to find the initial, or what? Let me check in the question. We need to find the moment of inertia of the disk. So yeah, pretty much initial. We need to find this, and we have somewhat of this. So let's just denote this I1. Let's denote the I naught into I1. Then what happens is I1 and omega 1 is given to us. Omega 1 is given to us, which is omega 1 is 10 by 3. 10 by 3 pi equal to I2 is I plus I1. You get it, right? Or you do not. Do you get it? I naught plus I1, yeah. Omega 2. Omega 2 is also given, by the way. So I1 times 10 by 3 pi equal to I naught, we just found, is 8.1 into 10 to the power minus 5 plus I1 is I1 times omega is 3 pi. Yeah, 3 pi. So out of all this, you can cut the pi and nothing else. So you multiply it, I think. Yeah, multiplying it is the best option right now. 10I1 by 3 is equal to 3 into 8.1 into 10 to the power minus 5 plus 3I1. Now this goes the other side. 10 by 3i1 minus 3i1 equal to 3 into 8.1 into 10 to the power minus 5. Or how much will this be? 10 divided by 3 minus 3. This will be 1 by 3. 1 by 3 I1 equal to 3 into 8.1 into 10 to the power minus 5. Or I1 will be equal to 9 into 8.1 into 10 to the power minus 5. So if we do 8.1 into 10 to the power minus 5 into 9, we get this will be 7.29 into 10 to the power minus 4 kg meter square. This is the answer of moment of inertia that you need. That is all you need to do to get the whole 3 marks. And this is a very long question, which means definitely it is going to come in 3 marks. So that's it for this type of questions. Now we are going to the third type, that is the type 3, which is conservation of angular momentum. So this is very easy type of question and we already did it just right. This is the thing. In these questions you have to find out everything else first and then use the conservation of angular momentum. But in this type of questions you simply use the conservation of angular momentum. So let's go. There are 2 questions given in the book and both of them are very important for 2 marks. So we are doing question number 2 of this type, and the question says a ballet dancer spins about a vertical axis. A ballet dancer spins about a vertical axis. Is it visible? Yep. About a vertical axis at 1 revolution per second. At 1 revolution per second, with her arms stretched. With her arms stretched. With her arms folded, her moment of inertia about the axis reduces by 40%. Calculate the new rate of a revolution. Okay, so now you are asked to calculate the new rate of revolution. The question says she revolves at this rate. Rate here means frequency. So solution of this question will be like a ballet dancer spins f1 will be 1 revolution per second, and that means with her arms stretched. So the moment of inertia is just I1 is I. Let's suppose let's say this I1 is I. In the second case, the F2 is to be found and I2 is 40% reduced. It is reduced by 40%. So it will be 40% reduced. So I minus 40% of I. You get it? So it will be like if you minus 100% of I, that will be 1 minus 40% of, that will be 60%. So this will be 60% of I. It is reduced to 60% of I. Then we just need to find the omega for that, but you cannot do that and just directly write from the principle of conservation of angular momentum. We know that I1 omega 1 equal to I2 omega 2, ensuring that I1 is I and omega 1 is 2 pi f1 equal to I2 is I into 60% and omega 2 is 2 pi f2. You can simply cut the 2 pi f2 and i's, and then we have f1 is given, that is 1 equal to 60% into f2, or 1 by 60% equal to f2. So if you do that, you will get somewhere around, let me do it, 60% is 0.6 basically, so you just do 1 by 0.6 and that will be 1.67 revolutions per second. This is the answer you need, and that's it. So we have completed all the types of questions given in the book. Now we are going to do a few exercises. There are 25 exercises given in the book, and we are going to do a few of them. Or do we? I do not think we need to do these questions. These are just the same as what we did. So there is no point on doing the numericals once again. That's it for the numericals of the chapter. There is no much left. Thank you for watching this video, and from next video we are gonna start the topic. Next topic, that is our, what is the next topic? Let me check the next topic. The chapter 2 basically. We have completed rotational dynamics. Now we're going to simple harmonic motion or periodic motion. Yeah, we're going to periodic motion, and that much is it. Thank you for watching this video.